PhD in 2012 from the University of California, Los Angeles, advised by Ciprian Manolescu. After the PhD, he was an RTG instructor at the University of Texas at Austin and a member at the Institute for Advanced Study before joining North Carolina State University, where he is now an associate professor. He has received the Alfred P. Sloan Fellowship and many other awards throughout his career, and we are delighted to have him speak to us about exotic four manifolds and fluor homology. And then one other note, if throughout the talk y'all have any questions, you should feel free to unmute and ask them, or if you prefer to put them in the chat, I will ask them for you. All right, take it away.
Great. Yeah, thank you all for the invitation to speak here. Thanks everyone for coming. I just think that this is a sort of fantastic format that the organizers put on. I think it's really valuable. It's a valuable service to the community. I wish something like this existed when I was a grad student or a postdoc. Okay, let's go ahead and get started. I should say everything I'm going to say today is joint work with Adam Levine and Lisa Piccirillo. And this is going to be mostly a philosophy talk until the very end. So probably most of what I say is not really true, but it's mostly true. And if you want any kind of real truths, then yeah, please feel free to ask questions. Okay, so let me start with a talk. And a talk should start with a bold claim. So let me start with a bold claim, which is the following: that smooth four-dimensional manifolds are very special. Okay, so that's my claim. And let me try to substantiate my claim with a proof. And so here's a proof that four manifolds are very special. And I'm going to prove this by telling you an old result of Stallings, which says the following. Let's say I have a smooth manifold of some dimension n. If this is homeomorphic to Rn, then actually it's diffeomorphic to Rn. As long as n is not equal to 4. So in all dimensions other than 4, being homeomorphic to Rn is the same thing as being diffeomorphic to Rn. That's kind of an amazing thing. There's nothing very special going on Euclidean spaces. But when you switch to dimension 4, things kind of go off the rails. And Taubes proved that there are actually uncountably many smooth four manifolds. Which are homeomorphic to R4, but not diffeomorphic to R4. And these are what are called exotic smooth structures on R4. So smooth manifolds which are homeomorphic to something we know, but not diffeomorphic. Okay, so that's in some sense a way that dimension 4 is very special. And not only does it behave very differently than higher dimensions or lower dimensions, we know very little about this. So, for example, we don't know all of the smooth structures on any four manifold. So I'll say we haven't classified all the diffeomorphism types for a given homeomorphism type. And in fact, maybe I should say, we know so little that we don't even know about the fourth sphere. We don't even know about the fourth sphere. So we have the smooth Poincare conjecture, which says that if X is homeomorphic to S4, then X is diffeomorphic to S4. and we don't even know this. So we have uncountably many smooth structures on R4. And if you add 1 point, you 1 point compactify. We don't even know how to produce any other smooth structures, but we don't know how to show there aren't any other smooth structures. So dimension 4 is it's just totally weird. And maybe sort of part of this philosophy is you could ask, well, is it hard because smooth four manifolds are hard, or is it hard because topological four manifolds are hard? And they're both kind of hard and interesting in their own ways. But I just want to point out kind of that sometimes it's very easy to know when topological four manifolds are the same. So kind of part of Friedman's work is that for simply connected four manifolds, the cohomology ring determines the homeomorphism type. So if you have two four manifolds, let's say they're simply connected, it's very easy to tell whether or not they're homeomorphic. You just compute the cohomology, which is usually not very hard. But on the other hand, trying to tell whether or not two things are diffeomorphic can be very difficult. And so I want to kind of mention a little bit of a major industry that had a lot of activity, maybe from the 80s to the, let's say, to the mid-aughts. There was a major industry which was, well, we don't know how to classify smooth structures, but maybe we can just go around trying to find as many different smooth structures on four manifolds as we can. And so there was this strategy for a while, which is, given your favorite homeomorphism type for a four manifold, try to cook up exotic smooth structures. So try to find four manifolds which are not diffeomorphic, but are homeomorphic. That's kind of the best that maybe that we could do, because I think people don't even have a good scheme for how you might try to classify smooth structures, let alone how to prove it. And maybe what's a little bit surprising is that this is actually harder to do on closed four manifolds. So if you have a manifold which is closed, it's actually usually harder to cook up an exotic smooth structure. So for example, we just said that this is open for the four sphere. We don't know how to cook up a new smooth structure on the four sphere, but pretty much all the simplest four manifolds you can think of, we don't know how to cook up exotic smooth structures. So we don't know about S4, we don't know about S1 times S3, S2 times S2, a connected sum of CP2s, all with the complex orientation. We don't know any aspherical examples.
And we have a question in the chat.
Okay.
Is there always a canonical non-exotic smooth structure on a given topological manifold, or are they all equally good?
Oh, that's a great question. Yeah, so if you have a topological four manifold, you might even get unlucky and it might not have a smooth structure. But sort of, okay, let's just talk about smooth four manifolds. I would say that there is some four manifolds are very nice and they have kind of a canonical smooth structure, maybe like S4, S1 times S3. Maybe you have a smooth structure that kind of admits a metric with a really nice geometry, like positive scalar curvature, or maybe like from Michelle's talk, maybe you have a metric that has a hyperbolic structure. So in some sense, it can be kind of canonical-ish that way. But sometimes you have different four manifolds, different smooth structures that maybe kind of have their own unique, interesting geometry. Maybe one is a symplectic structure, one has a positive scalar curvature metric. So I would say in general, there's sort of not a canonical choice. But I don't know, maybe if people have different opinions, they could blow up the chat with why, any given four manifold really has its own unique smooth structure. I'd be curious what folks think. Yeah, but that's a great question. Yeah, so in general, this is just, it's open for all kinds of very simple four manifolds. We don't know how to cook up smooth structures. And maybe I could say, as the four manifold in general gets simpler, if it's closed, it's harder to cook up smooth structures. So for example, the four sphere, or you can think of maybe aspherical four manifolds as kind of having some simple topology, or things with small Betti numbers. And maybe just to kind of give you an update on the state of the art, maybe I'd say something like the smallest known example, where smallest is, it's kind of subjective, but let's say measured in terms of the size of the second homology, is CP2 connects two CP2s with opposite orientation. And that was maybe about 15 years ago. And we don't have too many new examples of very small exotic four manifolds. So again, we could say, well, like how do you actually tell smooth structures apart? We have this Friedman's theorem that maybe tells us, okay, we could show that two four manifolds are topologically equivalent, but we have our candidate counterexample to the Poincare conjecture. How are we going to actually show that it's not diffeomorphic to S4? So let me kind of just talk a little bit about a classical strategy for kind of distinguishing smooth structures. And most of this basically comes from gauge theory. And again, this was very trendy in the 80s to the aughts. And the very loosely, the strategy is to try to study four manifolds by their surfaces. So you might think of studying, if you study mapping class groups, maybe you care about curves on surfaces. If you study three manifolds, maybe you think about knots inside of three manifolds. And for four manifolds, we really want to study surfaces. And what do I mean? How could you kind of quantify this? Well, maybe you try to look at the minimal genus of a surface representing, say, a given second homology class. So you say, okay, I'll pick my favorite class in second homology. What's the minimal genus of a smoothly embedded surface representing that class in homology? And if you've thought about things like the genus of a knot or the Thurston norm of a three manifold, in general, it can be kind of hard to minimize anything, to say, well, how do I know that what I have is actually the minimum? It's obviously an invariant in some sense, but why can you actually do anything? And just like the knot genus or any other kind of minimizing type numerical invariant, you want some other invariant that you can use to kind of bound whatever you're studying. And so the invariant that I'm going to talk about, I'm going to call it F, because this is vague and philosophical. And what F does is it takes in a smooth four manifold, and it's basically going to count the number of solutions to some PDE on this four manifold. Okay, and so this PD is maybe going to depend on a little bit of geometric structure on the four manifold. But what I do is I just write down some PDE and I just count the number of solutions in some sort of very rough sense. And the idea is that this is something about the global topology of the four manifold, but it knows about surfaces. And so in particular, understanding this numerical invariant, which I'll talk a little bit more later in the talk, this numerical invariant satisfies something called the adjunction inequality. And the adjunction inequality says, maybe in some kind of rough sense, that surfaces govern these invariants in terms of their Euler numbers. So I'll say if I have a homologically essential surface, S, inside of my four manifold, whose normal bundle has Euler number at least twice the genus of my surface, then this invariant has to vanish. So another way of saying it is basically if I have some surface, I perturb that surface a little bit and I count the number of self-intersection or the number of intersections of those two surfaces with sign. If that number is too big relative to the genus of the surface, then that makes my invariance vanish. So it's sort of, you can think of it as a local obstruction. If I see this local thing, a surface with a certain property, then that's obstructing me from having good solutions to this PDE on my four manifold globally. And on the other hand, if I want to say something globally, say the invariant is non-zero, then I might need some extra geometric structure. And so, for example, if my four manifold is a symplectic manifold or has a Kähler structure or some sort of nice enough geometric structure, then actually these invariants are non-zero. And hence can maybe governs the surfaces in the four manifold. They can't have sort of too many self-intersections. Okay, great. So let me just give kind of a sort of concrete-ish example to have in mind. It's not so important to maybe know what these four manifolds are, but I just want to illustrate that this can be useful for distinguishing four manifolds. So here's an example. I'm going to take 3 CP2s, connect sum them together with the complex orientation, and then I'm going to take 20 CP2s with the opposite orientation and stick those together. And you'll notice that inside of this, inside of any of those CP2s, I see a sphere with Euler number 1. Right, the P1 inside of P2, that has a neighborhood of that is a disk bundle with Euler number 1. And so by our adjunction inequality, we see that these invariants have to vanish. This is a nice simply connected four manifold. We can compute the cohomology of this thing. And it actually happens to have the same cohomology as a K3 surface with opposite orientation. So what's a K3 surface? Well, you can think of it as basically something coming from complex or algebraic geometry. It can be described as being cut out of CP3 by a degree 4 equation. It's not so important for the talk, but basically the point is I can write down this kind of nice globally defined kind of complex geometric object. And so it inherits a nice symplectic structure. And the invariant is not zero. So you can do some nice kind of algebraic geometry constructions to build some nice four manifolds. And you can compute that the cohomology ring of this thing is the same as the connect sum of CP2s on the left. And so these are homeomorphic, but not diffeomorphic.
We've got another question in the chat.
Great.
Does the normal bundle Euler number depend on the choice of smooth structure?
Does the Euler number depend on the choice of smooth structure? No, that doesn't depend on the smooth structure. But if I change the smooth structure, that surface that I had may not be smoothly embedded. So if I had if the surface was smoothly embedded in both smooth structures and represented the same homology class, then the Euler number would be the same. So it's some kind of combination of, okay, I look at this, the kind of algebraic topology tells me something about the Euler numbers, but the smooth topology tells me whether or not I can represent that surface by, represent that homology class by a smoothly embedded surface. Yeah, that's a great question. Okay, great. So this is kind of the idea, and this is what people have been doing for a long time and usually it goes in this kind of a way. Maybe you take some four manifold that has this nice global geometric structure, like a symplectic structure, and you maybe okay, maybe it's really big and you kind of do some cut and paste operations that respect this global geometry, like some kind of sort of symplectic surgery operations, whatever those are. But you do some tricks to basically make sure you can guarantee these invariants are non-zero, but you're kind of always keeping track of the sort of global structure. And kind of what I want to talk about today is how you can approach these invariants in a way that's a little bit more kind of low dimensional topology flavored, a little bit more cut and paste, a little bit more built out of handles. So the goal I want to give is maybe say a different four manifold invariant, a different even perspective on the same four manifold invariants using what are called TQFTs and Floer homology. And if there's some time at the end, maybe I'd like to say something about sort of how we could actually try to construct four manifolds, exotic four manifolds, using handle decompositions. So using kind of little, like less sort of global geometric constructions and more just kind of build your four manifold out of little itty bitty pieces. Okay. So that's the goal. And maybe I want this to be more of a proof of concept than, let me try to wow you with some results. And so I'll just kind of try to say a few of the things that come out of the more out of the philosophy than actually are sort of anything too terribly exciting or new. But I'll just tell you the kinds of things that you can do with the philosophy. So for example, we can cook up some exotic four manifolds with this, so sort of pairs of exotic four manifolds with the same cohomology with rational coefficients as a connected sum of CP2s. So at the beginning of the talk, I said we don't have exotic connected sums of CP2s all with the same orientation. Well, we can kind of get close to that, and the kind of ours have some pi1 equals z mod 2. You can cook up exotic four manifolds that violate the adjunction inequality. So let's say with Euler number 0 essential spheres. So you can tell things apart, even though these kind of classical invariants can't tell them apart. If there's some time at the end, then we'll cook up a four manifold, which is homeomorphic, but not diffeomorphic to S1 times S3, connect some CP2s and CP2 bars. And maybe if you're interested in surfaces in four manifolds, I'll just say that you can do things like cook up exotic surfaces inside of S4. So you could find embeddings of surfaces which are topologically equivalent, but not smoothly equivalent. Okay, so these are just some of the kinds of things you can do with this philosophy that I'm going to try to sell you on. That's kind of where we're going to go next, is just kind of a little bit of philosophy about how we can think about studying invariants of four manifolds, kind of using like a little bit of a cut and paste construction. But maybe I'll pause here and see if there are any questions. Great, pause over. Okay, so.
Can I ask a question, Ty?
Please.
You said for item 1, the pi1 was Z2. Do you know what happens if you pass to the double branch, the double cover?
Yes. So the double cover actually stops being a definite four manifold. Yeah. So, and in fact, that's actually how we tell these things apart, is like we build exotic simply connected things that have kind of lots of lots of cohomology, like B plus and B minus. And then there's some free involution on them.
Cool.
And yeah, that's a great question. So I think, and maybe this is like, if I can take this moment to sell my philosophy further, which is that like when you build things out of handles, you can get a little bit more control. So it's maybe easier to build things that have symmetries naturally with them. And so something that comes out of some of the constructions is very easy to see symmetries because you just can see how you're building this four manifold basically out of knots. And so it's easy to see symmetries. And then that kind of is what allows you to do things like cook up exotic surfaces or cook up, exotic sort of four manifolds with other pi1 and things like this.
Thank you.
Great, that's a great question. Okay, good. So now it's time for, if there hasn't been enough philosophy, then I'm going to give you more philosophy. So this is what people might call the TQFT perspective. And sort of there's a philosophy here, which is we want to break our four manifold into pieces, which are easier to understand. And that will somehow allow us to understand this invariant F, which I haven't told you very much about yet. And so I'm going to say it kind of, which is that F can be extended to what's called Floer homology. And very roughly, the idea of Floer homology is rather than just closed four manifolds getting maybe numbers, we're actually going to take in three manifolds. So suppose I have maybe some three manifolds closed and oriented. And what we're going to spit out is, let's say, some finite dimensional vector space. And morally, what you can think of this as is it's the homology of a chain complex, which is generated by solutions to basically the same PDE we were working with before on the four manifold. You can write that PDE down on the three manifold, and basically you kind of build a vector space out of the solutions to the PDE on the three manifold. Sounds like we didn't really make our lives any easier, but I'm going to hopefully convince you that we made our lives easier by doing this. And what's nice about this theory is that if we have a cobordism, so we have some four-dimensional manifold, and let's say its boundary has these two pieces, y and y prime. So some four-dimensional compact four manifold with boundary basically y disjoint union y prime. This gives us actually a linear map between the vector spaces. And it satisfies some nice properties, so that basically it's a functor from some kind of cobordism category to the category of vector spaces. And what that means is that if we take the invariant for y times I, that just gives us the identity. And if we glue two cobordisms together along their common boundary, say W1, W2, then the associated map is the composition. So normally when we think of functoriality for something like singular homology, that behaves well with respect to induced maps between spaces, induced maps on homology. And now our sort of morphisms, so rather than functions between spaces, are cobordisms between three manifolds. So associated to a cobordism, we get a map, and it behaves nicely with respect to that. Okay. So how does this relate to closed manifolds? So maybe I'll say if X was a closed manifold, so if X is closed, then I think of X as a cobordism from the empty set. And so F of X really goes from F of the empty set to F of the empty set. Now that's basically turns out to be our ground field that we're working over for these finite dimensional vector spaces. And this just ends up being multiplication by exactly that number we were talking about before, the number of solutions to our PDE. And so basically what we're doing is we're taking this global count of solutions and we're kind of breaking it up into little pieces. The three manifolds, we count solutions on there. The cobordisms, we actually count some solutions to the PDE on the four manifold with some asymptotics to the three manifold, solutions on the three manifolds at the end. It doesn't really matter so much for the purposes of this talk, but basically we're taking this whole closed four manifold invariant, and we're breaking it up into little pieces that we can study just using vector spaces and linear maps. So that's kind of nice. But again, it's kind of like things got harder. We went from trying to count solutions to a PDE to building a chain complex built out of solutions to a PDE. So it seems like things got worse. But actually, it turns out that this theory is actually much more computable once we start looking at three manifolds. So F of three manifolds is very computable. And it's likely if you're sitting in this talk, you know some techniques for computing these invariants because they kind of have all kinds of connections to things like contact topology, maybe surface dynamics, hyperbolic geometry, knot concordance. Character varieties. So basically, if you have a way you like to think about low-dimensional topology, there's kind of a way of computing Floer homology for some kind of three manifolds that you might be interested in. And I could keep going on this list, but I think that's a long enough list. So it's very, very computable, depending on the, whatever kind of three manifolds you want to compute. There's lots of different options. And maybe I'll just give some examples. And there are sort of various flavors, various versions of these Fs, maybe depending on whether you like contact topology or you like character varieties or you like symplectic geometry. But I have one in mind, and for my F in mind, it's sort of trivial on S3. Most of these things are trivial on S3. If you are a Floer homology expert, maybe think instanton Floer homology, or think reduced Heggard Floer homology. And then you'll get that the invariant of S3 is 0. But actually, for most three manifolds, this invariant is very non-zero. So for example, if I take a knot, let's call it K, and I do a surgery on that knot, and what does a surgery mean? It means I remove a tubular neighborhood of this knot, and I glue back in a solid torus. And the number is going to tell me how I glue back in this solid torus. I'm going to send the meridional disk of the solid torus to something which corresponds to minus mu plus lambda on the knot complement. Okay, if you haven't seen Dane surgery, it's not so important. All you should imagine is you take a knot, you remove a tubular neighborhood, and you re-glue it up with a twist. And there's some way of associating a number to how I re-glue. But this Floer homology actually knows that this thing is always non-zero as long as my knot is not unknotted. So for any non-trivial knot, what I can do is do this surgery construction, build a new three manifold, and the Floer homology basically always knows that it's non-trivial. Floer homology also can tell you whether or not your three manifold fibers over S1. It knows the Thurston norm. It knows all kinds of really nice properties of the three-dimensional topology. And we said before, having some global structure helps us know about computing this invariant for closed four manifolds. But local structure can also be very good. So I'll say that if we have a cobordism, let me call it like f of W4, this is very computable. This is very computable when W is let's say, a single handle attachment. And for the purposes of this talk, let's just talk about two handle attachments. Okay, so what is a two handle attachment? So what you should think of that as is it's just actually a thickened two cell attached to three manifold. And so this is just specified by a knot. And an integer. So basically the framing or how to thicken up that two cell. And just again, as an example to illustrate that we do know a decent amount about these Floer homology theories, let's start with that three manifold that I just told you always has non-trivial Floer homology. And I'm just going to attach a very simple two handle. I'm going to attach a two handle along a meridian with some way of thickening it. And if I pick the right way to thicken it, then I actually always get an isomorphism. Again, for the experts, you have to be a little bit careful with this. This is going to be true in Floer's original version of instance-on Floer homology. If you're a Heegard-Floer homologist, then maybe the exercise is to modify the statement to actually be true. But the point is that, don't worry if you don't know what these four manifolds are. The point is that for very simple manifolds built out of simple pieces, we can really analyze what these maps are. Okay, great. Maybe I should just stop for a minute because that was just a lot of philosophy. Are there, any questions about the sort of general Floer homology picture? Okay, so then maybe for the last part of the talk, what I want to do is I want to kind of see how we can get a new perspective on computing invariance of four manifolds. So maybe we can see that from, maybe I should actually go back here for a second to where we were defining this Floer homology. Maybe you can see that from, let me highlight this, from this perspective. This kind of tells us that if we take a big closed four manifold and we break it up into little pieces and we compute the cobordism maps for each of those little pieces, then we can compute our global invariant of our four manifold here. But in general, that can still actually be, I don't know, oftentimes you do this and you just get zero and you're sad. Or somehow it is very, might be very difficult to, maybe your map is an isomorphism, or something about the structure of the map, but it's maybe hard to compose two cobordisms together because the way you glue the ends up could be some complicated automorphism of the three manifold or something like this. It can be a little bit hard to keep track. And so what I want to do is give a slightly, let's go here. I want to give a kind of slightly different perspective on using this TQFT structure to study four manifolds and study these invariants. So here are some new invariants. And what I want to do is I want to change the philosophy. So the philosophy before was let's look for surfaces. Surfaces told us something about four manifolds. But I want to say let's look at three manifolds. Let's look at three manifolds inside of four manifolds. So we're looking at codimension one things. And so let me try to define a new invariant. So let's say I have some closed four manifold. And for simplicity, let's assume that B1 is 1. And so let's say I have some 4 manifold with B1 equals 1. And so schematically, it kind of looks like this, X. And I can pick a generator of H3. So H3 is also rank 1. I can pick a generator of H3, which is a non-separating hypersurface, some 3 manifold, and I can ask about that. And so what I'm going to do is I'm going to define some invariant, I'll call it alpha, which is going to be the minimum of the dimension of all possible f of y's. So here I'm minimizing over all the possible y's that sit as a non-separating hypersurface. So minimize over y, which is a non-separating hypersurface. In other words, I want the Poincare dual of that, the class of that y in h lower 3 to generate h upper 1. And so I minimize over all these things. And then maybe you're unhappy because we had some discussion about how it's hard to minimize things. We were talking about minimizing genera of surfaces in a class in H2. And now I've said, rather than trying to minimize the genus, I've tried to say minimize the count of solutions to some PDE. It sounds like things got a whole lot worse again. But what I want to convince you of is actually this can be kind of computable. And so there's some kind of approach to studying 4 manifolds by looking at the 3-dimensional hypersurfaces. So let me give an example. So maybe my example is, let's let X be just a 3-manifold times S1. And maybe I'll take B1 of Y to be 0 so that I get a 4-manifold whose first Betti number is 1. And my claim is that actually we can compute this invariant. We can figure out what sort of the minimal dimension of the Floer homology is of any non-separating hypersurface. So we're learning 4-dimensional information actually just with 3-dimensional information. So it's actually just going to be the dimension of the Floer homology of the 3-manifold we're using. And so let's actually prove this. Maybe we can give a proof of this so that I've actually proved something concrete in this talk. So let's suppose that we have some 3-manifold inside of our 4-manifold y times S1, which is supposed to be realizing the minimum dimension of the Floer homology of some non-separating hypersurface. So here's our picture. Here's y times S1. Here's maybe y. And maybe I have some weirdly embedded z like this. Somehow embedded in there in a really weird way, but has really small Floer homology. What I'm going to do is I'm going to pass to the infinite cyclic cover. And that looks like this. It's y times r. And I see a bunch of copies of y. And I see some copies of z. But the copies of z lift like this. And so actually what we're able to do is we're now able to see that z lives inside of y times I. Let me kind of try to draw that a little bit more clearly. So I have a cobordism, let's call it W1, that goes from y to z, and another cobordism W2 that goes from, let's see, W2 goes from Z to Y. And if I take W1 together with W2, I get Y times I. But this, okay, so who cares, right? Who cares? Why is this helpful? Well, what we do now is we think about what are our properties of being a T of this Floer homology. What do they tell us? Well, we know that the Floer homology of Y times I, that cobordism map is supposed to be the identity map on F of Y. And we said that if I glue two cobordisms together, then the associated maps are the composition. And so now that's telling me that my cobordism map factors through the Floer homology of Y. And so that tells me that the dimension of F of Z is at least the dimension of F of Y, which gives us a lower bound for this minimum. But this F of Z was the thing that was actually realizing the minimum. And so now, that's kind of nice. That tells us that our F of Y has to be the minimizer, actually. Okay, so this kind of tells us that there's some means of computing these invariants in some feasible way. And I'll just say that this can be generalized a little bit more. So if I look at some manifold like X, and I have some 3-manifold Y, and I think of X as being a cobordism from Y to Y glued up at the ends. And so if I know that F of W as a map from F of Y, sorry, we seem to be having a bit of a glitch. Can people see and hear me?
Yeah, I can see and hear you.
Oh, very interesting. Okay, my computer thing isn't working. Let me see if I can, sorry. Let me try to switch very quickly. Okay, I'm sorry. That's it. Can people see something? Great. Okay, so I'll just maybe finish by just saying the last remark that I was going to make, which is, yeah, so if you can actually go ahead and get that the cobordism map is an isomorphism, then you're able to compute the invariant of a closed Floer manifold. And in terms of the dimension of this Floer homology, and so maybe just the 30-second thing is that if you want to construct some kind of exotic Floer manifold, there's a strategy, which is to build some self-cobordism of 3 manifolds for which the map on Floer homology is very interesting. And that will tell you something about the invariant of the closed up Floer manifold. So knowing something interesting about the 3-dimensional hypersurfaces tells you something nice about the closed Floer manifold. And I just want to say that you can do this in a very explicit way. So I just maybe finish this talk by pointing out some picture of a drawing of an exotic Floer manifold, which just looks like this. So this gives you kind of you can just draw this nice picture, and it gives you a self-cobordism from some 3-manifold to itself, just by attaching these 2 handles along the blue, green, and purple curves. And you can actually compute that the map on Floer homology is an isomorphism, just very explicitly. And somehow, so that tells you something, you're able to compute the invariance of the closed up Floer manifold. And then you can just check that this thing has a different invariant than some simple Floer manifold like S1 times S3, connect some with some CP2s and CP2 bars. maybe the details of it aren't so important, but just the point is I want to emphasize that you can do things very explicitly. You can draw nice pictures, you can compute these invariants, and that's some way that you can actually go ahead and construct exotic smooth form manifolds. Okay, so maybe since my computer is breaking right now, this is a good place to end the talk. Sorry to have to run through the slides at the very end.
Are there any questions? I'll start by reading one from the chat and then I will open the floor to other questions. The question in the chat says, it looks like the cobordisms in your argument about y times S1 can be done in either order, showing that f of y equals f of s for any embedded surface. Is this true?
F of y, would it be possible to clarify what's being meant by f of s for a surface? Or I think I missed where the surface is.
Oh, okay, that's my question. So maybe I used the wrong terminology. This was a little new to me, but I didn't mean surface. I meant hyperspace.